Okay, in this screencast we're going to look at how gravitational potential energy and kinetic energy interact in something like a roller coaster ride. Now, in a situation where you've got something moving in a gravitational field like this roller coaster, then the total amount of kinetic energy will remain constant. So the total mechanical energy is constant. Now, by total mechanical energy, I'm talking about its kinetic energy, its gravitational potential energy, and its elastic potential energy. So whatever kinetic energy it has, plus whatever gravitational potential energy it has, plus whatever elastic potential energy it has, will always equal a constant. That is provided no other energy enters the system. Whoops, I misspelled constant. So no other energy is entering the system or leaving the system. So it's an isolated system, and within this system, the total amount of energy will be constant. Now, in a roller coaster, we haven't really got any springs happening, and so we can sort of disregard the elastic potential energy part because that's to do with springs. But because this object is going to be moving up and down, and it's going to be moving up and down in the gravitational field, certainly kinetic energy and gravitational potential energy will be there. Now, what we're saying here is whatever energy it had to be, the total amount of energy it started with at position A, now there's a total amount of kinetic energy and gravitational potential energy it has here, that'll be the same throughout the entire journey. So wherever it is in its journey, no matter where it is, its combination of kinetic and gravitational potential energy will always add up to the same amount. By the way, we're also assuming here there's no friction. Okay, so no energy is lost to friction. Of course, we remember that energy lost to friction causes heat. Now, let's do an actual example, worked example. Let's say that our roller coaster here is 200 kilograms, and we want to find out at the very top of the roller coaster, it's at rest, and we want to find out what's its speed at the bottom of the roller coaster here at B. Then, as it climbs up to this little hill here, what's the speed at position C, and finally D. So to begin this problem, we just need to establish how much energy, how much mechanical energy it has to begin with. So the total kinetic energy in this scenario, remember we can ignore elastic potential energy, is going to equal whatever kinetic energy it has plus whatever gravitational potential energy it has. Well, if it's not moving, then its kinetic energy will be zero. So at the very beginning of the journey, all of its energy is in the form of gravitational potential energy. And we can calculate gravitational potential energy as mgh. So it's going to equal mgh. Once again, let's take g equals 10 just to simplify the calculations. So it's going to be 200, which is the mass, times 10 times its height above the ground, which is 30. So it's going to be 2,000 times 30, which is going to equal 60,000 joules. And so that is the amount of gravitational potential energy it has at position A. And remember, it has no kinetic energy at the moment. All right, so now let's now imagine that the roller coaster is now released. So it now rolls down the track obviously it's going to gain speed until right down the bottom it's going to be travelling at its maximum speed. And we know it's going to be at its maximum speed because at the bottom of the track, it's now at ground level. In other words, its height above the ground is 0. So that means, if we look at its gravitational potential energy here, remember the gravitational potential energy is mgh. If h equals 0, then GPE will equal 0. So the gravitational potential energy at the bottom is going to be 0. But remember, the total mechanical energy must always be the same throughout. And we established at the very beginning that the total amount of mechanical energy that this card has at the very beginning was 60,000 joules. So, at the bottom of the journey, if the gravitational potential energy is 0, then all of the energy must be in the form of kinetic energy. And so we can now assume, or infer, that the kinetic energy is equal to 60,000 joules. So all of the energy is in energy of motion, which means we can now work out its speed, because we know the formula for kinetic energy. So remember, kinetic energy is a half mv squared. So we can rearrange that, and that formula rearranged is V equals the square root of twice the kinetic energy over the mass. And so to work out the speed of the roller coaster at the bottom of the roller coaster track is going to be 2 times the kinetic energy it had, and by the way this is at position B, kinetic energy at position B, it's going to be 2 times 60,000 divided by its mass, which is 200. So if we work that out, 2 times 60,000 is 120,000. And dividing that by 200, so we cancel out those zeros. 1200 divided by 2 is going to be 600, and so that's going to equal the square root of 600. And if we work that out, that's going to be 24 point, actually I'm just rounding up, 24.5. meters per second. So guess what? We now know that the velocity of the trolley at the bottom of the track at B is going to be 24.5 meters per second. Okay, so what's going to happen at C? Well, at C, it's gaining height again. So, because it's gaining height, it's going to gain gravitational potential energy. And if it's going to gain gravitational potential energy, that means it must lose kinetic, because remember, both of those must add up to a constant for this particular scenario. So, if we can work out now how much gravitational potential energy it will have at C, because it's gained height, that will also be equal to its reduction in kinetic energy. So, to work out the GPE at C, it's going to be mgh, which is going to be its mass, which is 200, times 10, but this time the height is 12. So it's going to be 200 times, so it's going to be 2,000 times 12, which is going to be 24,000. So we now know that at position C, it's got 24,000 joules of gravitational potential energy. But because, remember, at every point in the journey, including C, its kinetic energy plus its GPE must equal a constant, and remember in this particular problem the constant is 60,000. So if we now know that the gravitational potential energy is 24,000, then the kinetic energy must have reduced from 60,000 down to 36,000. Remember, kinetic energy is measured in joules, of course. So we can now work out the speed of the roller coaster at position C by using this value of kinetic energy. And so at C, we know that the velocity is going to equal the square root of twice its kinetic energy divided by the mass, which is going to equal the square root of twice 36,000 divided by 200. That will equal the square root of 72,000 divided by 200. Zeros cancel, so 720 divided by 2, which is going to be the square root of 360, I believe. So that will equal the square root of 360, and the square root of 360 is 18.97. Well, we'll make that 19. So it's 19 meters per second. So see what's happened? It started here, velocity was 0. Again, as it went down the ramp, got to position B, which was its maximum speed of 24.5 meters per second. But as it climbed back up the hill, it slowed down again to 19 meters per second. Now you can probably predict what's going to happen here when we get to D. When it gets to D, once again the GPE will be 0, which means all of the energy, all the mechanical energy will be in the form of kinetic energy. And so its speed here will be exactly the same as the speed it had at position B. Now remember, this scenario assumed no friction. If friction was acting, then all along the way, what would be happening, it'd be a certain amount of the energy would be converted into heat, and that of course would reduce all these values, because we're getting some of the energy we've got is being lost in the form of heat. But in this scenario, that's not occurring. Okay, thank you very much.